Good morning. My name is María Amorós, and I'm going to present a joint work with my colleagues Alonso Sepúlveda Castellanos and Luciani Cuos. The title of our work is the Isometry-dual property for 1-point and for 2-point algebraic geometric codes. A linear code C is a linear subspace of Fq to the n, where Fq is the finite field of Q elements. For some Q, which is the alphabet length and which necessarily is a power of a prime, and for some n, which is the code length. As an example, we have the double repetition code in F3 to the 4. In this case, we have words of length 4 and whose coordinates are all elements in F3. This is the double repetition code because in each word, the second coordinate is a repetition of the first coordinate and the fourth coordinate is a repetition of the third coordinate. It's easy to check that this is indeed a linear code. We say that two codes are x isometric for some fixed x vector in Fq to the n with non-zero coordinates, if D can be obtained as the set of words which are the bitwise product of the words of C by the fixed vector x. As an example, the code that you can see here is 1212 isometric to C. Now, suppose that we have a sequence of subsequently included codes from C0 up to C sub n. By this, we mean that C0 is included in C1, C1 is included in C2, and so on. One can prove that the dual code of Cn will be included in the dual code of C sub n-1 and so on. And we are interested in these sequences of codes for which C sub 0 is x isometric to the dual of C sub n, C1 is x isometric to the dual of C sub n-1, and so on for one same fixed vector x. Hence, we can give this definition. A sequence of codes C sub 0, C sub 1 up to C sub n, which are subsequently included, is said to satisfy the isometry dual condition if there exists a vector x with non-zero coordinates such that C sub I is x isometric to the dual of C sub n minus I for any possible I. Now we move to the area of algebraic geometric codes. We suppose that we have n different rational points which we denote P1 up to Pn, together with an even different point Q. Those all are rational points of a projective, non-singular, geometrically irreducible curve with genus G. For a non-negative integer n, define L of MQ as the set of rational functions that only have poles in Q of order at most n. Then one can see that L of 0Q is in L of 1Q, which is included in L of 2Q, and so on. Now we can define the code C sub n as the set of vectors which can be obtained as the evaluation of functions in L of MQ in the rational points P1 up to Pn. We consider the sequence of code C sub 0, which is included in C sub 1, which is included in C sub 2, and so on. The Weierstrass semigroup at Q is defined as the set of positive integers m such that L of MQ is different than L of m-1Q. to this set we add the 0. The Weierstrass semigroup is indeed a numerical semigroup because it contains 0, it's closed and under addition, and the complement of the Weierstrass semigroup in the set of positive integers is finite. In fact, the number of elements in this complement is exactly G, which is the genus of the curve. Once we have the Weierstrass semigroup at Q defined, and taking our codes into account, we define W star as the set of indices M such that Cm is different than C sub m minus 1, and we add the 0 to this set. This set is finite, and we call its elements from M1, which is 0, to M sub n. Obviously, W star is a subset of W, and we have a nice theorem by Olaf Geil, Carlos Monuera, Diego Ruano, and Fernando Torres, which states that if n is at least twice the genus plus 2, then the complement of W star in the Weierstrass semigroup satisfies that if we add an element of the Weierstrass semigroup to an element of this complement, we obtain again an element in this complement. Also, the sequence of the 0 code together with C sub m minus 1 up to C sub m sub n satisfies the isometry-dual condition if and only if the number of elements in W star plus twice the genus minus 1 is in W star. We can revisit all the results in terms of ideals of numerical semigroups. For this, we need to define what is an ideal. An ideal of a numerical semigroup S is a subset I of S such that I plus S is included in I. The Frobenius number, or the leader of the ideal, is the maximum of the complement of the ideal in the set of non-negative integers. As we proved with Quan Q Lee and Albert Vico Othon, the Frobenius number of an ideal is at most twice the genus minus 1 plus the number of elements in the complement of S of the complement of I in the semigroup S. An ideal I is a maximum sparse ideal if it attains this bound. And now we can restate the theorem of Geil, Monuera, Ruano, Torres in terms of ideals. If n is at least twice the genus plus 2, then the set W minus W star is an ideal of W, and also the sequence of codes 0, C sub m1 up to C sub m sub n satisfies the isometry-dual condition if and only if W minus W star is maximum sparse. Now, we want to analyze the same sequences of codes, but not defined only on one point Q, but in 2 points Q1 up to Q1 and Q2. Hence, we consider as before P1 up to Pn and Q1, Q2 to be different rational points of a projective, non-singular, geometrically irreducible curve with genus G. Now, for a pair of non-negative elements A, B, we consider L of A, Q1 plus B, Q2 to be the set of functions that only have poles in Q1 and Q2 of order at most A in Q1 and B in Q2. Now we fix B and consider the sequence of linear spaces L of 0Q1 plus BQ2, which is included in L of 1Q1 plus BQ2, which is included in L 2 times Q1 plus B Q2, and so on. And we can define as before the codes CAB as the set of vectors which can be obtained as the evaluation of functions in L of AQ1 plus BQ2 in the points P1 up to Pn. Again, CAB is a linear code, and we are interested in the sequence of codes that we obtain when we fix B and consider C sub 0B, C sub 1B, C sub 2B, and so on. Notice that when B is 0, we are in the previous case. We are in the case of exactly 1 point codes. Now, we define the set HB. This parallels the definition that we gave of the Weierstrass semigroup. This set HB contains 0 together with all non-negative integers A, such that L of AQ1 plus BQ2 is different than L of A minus 1 Q1 plus BQ2. We define also HB star as we defined previously BW star as the set of non-negative integers A such that CAB is different than CA minus 1B. We also add the element 0 in this set, and this set is finite as before. In this case, we call the indices in HB star as A1, A2, and so on up to AR. Obviously, HB star is in HB, as before we had W star was in the Weierstrass semigroup, but now HB is not a numerical semigroup in general. But still, we can state some properties on HB and HB star. Let's look now an example. In this case, we take the norm trace curve given by the equation y to the 7th plus x to the 4th plus x squared plus x equal to 0 over the finite field of 8 elements. We distinguish the point Q1, which is 1, 0, 0, the point Q2, which is 0, 0, 1, and take the other 31 points as evaluation points. In this case, the genus of the curve is 9. In the graph, we depicted in the y-axis the values of B, and in the x-axis the values of A. For each AB in the graph, we put a circle if A belongs to HP, and we put a star if A belongs to HB star. In our work, recall that we fix a B and see how the codes vary when we vary the A. So we are considering this graph and we analyze horizontal lines in this graph. Each horizontal line corresponds to a sequence CAB with a fixed B and a varying A. If we look at this graph, for instance, let's take B equal to 35. What this graph means is that H sub 35 has all non-negative integers, and H35 star contains exactly 0, 2, 3, 6, 7, and 10. This would be H35. What we can observe in this graph is that, first of all, that all stars are included in circles. Another thing that we can observe is that we can draw two diagonals, and below the lower diagonal there is an exact coincidence of circles and stars. Another thing that we can observe is that for each horizontal line the maximum star is attained between the lower diagonal and the upper diagonal. This is exactly what we stated in these lemmas. For a fixed b, we have that HB star is included in HB, and also that for all values of A below the lower diagonal, we have that H is in HB star even only if A is in HB. The second lemma is related to this maximum of HB star, which we saw that was between the lower and the upper diagonals. The first point of the lemma gives us the upper bound on the maximum of HB star, and the second point gives us the lower bound of HB star corresponding to the lower diagonal. In our work, together with Alonso Sepúlveda Castellanos and Luciani Cuos, we extended that theorem of Munuera, Gale, Ruano, and Torres, and we stated that if n is at least twice the genus plus 2b plus 2, then the sequence of codes given by CA1, CAN together with 0 satisfies the Isometry-dual condition if and only if n plus twice the genus minus 1 minus twice b belongs to H star sub 2b. Here we have to add these two here. Notice that in the case b equal to 0, which was the case of 1-point codes and which was the case of Gael, Munuera, Ruano, and Torres, we don't need these two here because it's the same 0 or 2, 0. But once we have non-zero b's, then we need to add these two here. So notice that also this number here is exactly the upper bound that we saw for H star. We saw that the maximum of HB star is at most n plus 2g minus 1 minus b. So if here we say that n plus 2g minus 1 minus 2b is in H2b star, this means that H2b star, its maximum, attains the maximum given by the bound. So we have the Isometry-dual condition in if and only if the set H2b star attains its upper bound. This is shown again for the same curve. In this case, we draw a horizontal line. This horizontal line states where our theorem holds. Our theorem holds below the horizontal line because it only holds when n is at least twice the genus plus 2b plus 2. So it holds only when b is at most n minus 2g minus 2 divided by 2. In this case, what we proved is that the sequence of codes given by each of these horizontal lines, given by, in fact, the stars in each of these horizontal lines, is indeed an Isometry-dual sequence of codes if and only if the given b satisfies. For instance, here the b is 3. This 3 satisfies that H6, we need to move to 2b. From 3, we need to move to 6. H26, which corresponds to the H star 2 times 3, which corresponds to the stars in this horizontal line. This set attains the maximum, and indeed this star corresponds to the maximum given by the upper diagonal. This is why here we have an Isometry-dual sequence of codes. For the other cases, we do not have Isometry-dual property because if we go to twice the b corresponding to the horizontal line, we get to an H2b star set that does not attain this maximum given by the bound. We analyzed our results over a Kummer extension given by the formula y to the n equal to f of x, where f of x is a separable polynomial of bounded degree. In this case, the 2 points are the point at infinity and the point corresponding to a root of f. We define CAB as before. In this case, for evaluating functions in L of A, P infinity plus B, Q, where Q is this point corresponding to a root of the polynomial f. We investigate, as before, the sequence of codes given by a fixed B. In this case, and using a theorem of Mahara, we could determine exactly what is HB star and also what is the maximum of HB star. They are given by these formulas you can read in this slide. From these results, we can deduce this theorem. For a given V, which is bounded between 0 and n halves minus g minus 1, we consider the set of indices A0 up to AS as the set of elements in the set that contains HB star intersection 1 up to n plus twice the genus minus 2b together with 0. In this case, the corresponding sequence of algebraic geometry 2-point codes is X isometry-dual for some vector x if and only if n divides twice b plus 1. We illustrate now the previous theorem with an example. In this case, we take the Hermitian curve with equation y to the 5 plus x to the 4 plus x equal to 0 over the finite field of 16 elements. In this case, you can take Q1 to be 1, 0, 0, Q2 to be 0, 0, 1, and we have n more points with n equal to 63. In this case, the genus equals 6. What the previous theorem stated is that the bits for which we have an isometry-dual sequence of codes, that is, the bits for which this horizontal line corresponds to the indices of the codes in an isometry-dual sequence of codes, are exactly those bits for which n divides to b plus 1. In our case, n is 5 because it is the index of y. So we have isometry-dual sequence property if and only if 5 divides to b plus 1. This is only possible if b is equal to 2, 7, 12, 17, 22, and no more, because then we get out of the limits of our theorem. And with this example, we finish our talk. Thanks for your attention.